typically used for things like image processing and object detection and so on. So there are a couple different ways you can build an accelerator for a convolutional neural network on FPGAs. So one is that you could make some kind of generic processing element. So it's got some multipliers, it's got some adders, it's got some muxing to allow you to move data around, etc. And it's relatively generic, and you can use it for all of your layers. So you build a whole bunch of these processing elements, they're communicating together, they've got some buffer RAM, and you take maybe the first layer in your neural network, so maybe it's a two-dimensional convolution with a 7x7 filter size, and stride 2 means you move the filter over 2 pixels every time you complete one output. And you basically map that layer using these PEs. So these PEs, you control the control logic, sets their muxing, etc., so that they implement what this convolution needs. After you're done that convolution, you've got some temporary data stored in this buffer, and you need to go on to the next layer of the neural network, and it's different. So maybe this is another two-dimensional convolution, but it's got a 5x5 filter size, so this filter's smaller. The convolution is doing smaller. The stride is 1, so it's producing now one output value for every one of the input locations in your image or feature map. And you map that to these PEs. So you set the muxes and control logic differently, and they go through that layer. And so on. We go on to the next one, and it's got an even smaller filter, 3x3 kernel size. So that's one way we could build our hardware. We could build it with these more generic PEs that we want some parallelism, so we usually build a whole bunch of them communicating, and they have enough flexibility, which basically means muxing or sometimes extra hardware that's only used sometimes, so that they can do any one of these layers. Okay, but that costs you some efficiency. So the architecture I'm about to show you, HPipe, doesn't do that. Okay, so it takes a different approach. Basically, it creates a different PE for every one of these layers. So you can see you've got 3 different colors of PEs here. So each of these layers maps to a specific PE that we've built inside of the FPGA. And those PEs just feed data to each other. Okay? So they form basically a coarse pipeline. This PE is processing this layer and then feeding its data onto the next layer, which is actually implemented by a different PE, different hardware, specialized to this exact 5x5 kernel, and then feeding that onto the next PE, which is specialized to this exact 3x3 kernel. The design style that HPipe uses between these PEs is a latency-insensitive communication channel. So that's basically a data flow architecture. It's one of those streaming data flow models with ready and full signals, basically. Like the ready valid signaling that you're using in assignment 1 and assignment 2 is what it's using as well. And it has FIFOs at the input to each of these PEs so that it can buffer up some data. So it's using exactly one of the programming models that we talked about. So it's exploiting pipeline parallelism a lot. Each of these PEs is deeply pipelined with just regular registers. And then in between the PEs, we're basically pipelining between the layers with FIFOs and ready valid signaling. So what's called a latency insensitive pipeline. So we're using 2 different streaming models. Simple one inside the PE, and this sort of more flexible one where you can actually stall and you have FIFOs in between the PEs. Does that make sense? Is everybody with me so far? And if there are 50 layers in the neural network, you wind up with 50 different PEs, all implemented in the chip. So what does this look like? Let me move this out of the way so you can see it better. So this is a picture of a particular neural net. So this is MobileNet V1 plus SSD. SSD stands for single shot detector. It means it's got some extra layers that are used for object detection. So MobileNet is a particular CNN that researchers have developed that's good at image classification. But it turns out if you add some additional convolutional layers and a bit of post-processing logic, you can do more than just classify images. You can actually detect objects and classify all the objects. So that's what this is doing. And what you can see here is here's where your input comes in. So this is the first layer. And a few of them are labeled here. So here's the 18th layer, which is a two-dimensional convolution. Here's the 16th layer, which is a different two-dimensional convolution. So it's in purple here. The other one was in green. And there are many other layers here. They're not all convolutions. You know, some are ReLU units, so rectified linear units. Some are, averaging layers, all sorts of things, okay? And you can see there's distinct hardware for each of them kind of interleaved throughout the chip. And the pipeline of data just kind of flows through this. You know, I just made that up, right? The CAD tool, though, tries to keep things that are connected together. So the pipeline would tend to thread through these units in kind of a connected way. Okay, so that's what it looks like when it's implemented. I'm going to show you results that this is quite efficient. You gain efficiency by basically specializing these PEs to each layer. So that's a good thing. But there's a down thing from a productivity point of view. We need a different, like this hardware implements exactly this neural network. If we want a different neural network, we've got to redesign the hardware. If you did that by hand for every neural network that interests you, you're going to be doing it for a long, long time. Okay? So we need to build some automation. And the automation that this project or this accelerator uses is shown here. Okay? So it's what's called a domain-specific compiler. So domain-specific compiler just means I generate hardware or software, or both. I generate a system, but I don't do it for arbitrary C. I'm not trying to do all possible systems. I'm trying to do it for a certain domain, a certain group of systems. So this one is, the domain is basically convolutional neural networks. So it takes in two inputs, specifications of the hardware. So basically, how many resources are available in the FPGA you want to target? How much RAM, how much DSP, how much logic? And it takes in a description of the neural network. And that's in TensorFlow format. So TensorFlow is one of the popular frameworks for training neural networks, working with them. So it can output the model, the neural network architecture that you're using, and that goes into this flow. So then what happens is it does first a graph optimization step, which is relatively simple. It's basically you just have a bunch of layers that are arranged in some sequence. That's your neural network, and you have parameters on those layers. Like this layer is a traditional convolution for neural networks. This one is a point-wise or a depth-wise. There are a few different kinds of layers like that. So you have that additional information, and you have a graph that describes which layers feed what other layers. Okay, so the first thing we do is there are just some optimizations that can be done where we just make a few reordering of nodes that feed each other, sometimes collapsing two nodes together, that turn out to just make it easier to generate hardware. So I think you had a question. Yeah, go ahead.
So for the TensorFlow description, like what kind of form?
It's a TensorFlow frozen graph, and that's basically how it was written by Matthew Hall, the graduate student who created this, and I can't tell you much more than that because I've never gone and looked at like what does that actually mean in terms of parsing this thing in. Does that make sense?
It's not Python code or something like that.
It's not best on.
It's not Python code or something like that.
I haven't gone and looked at like what is the low-level format of a TensorFlow frozen graph. I assume it's some binary format, and then you basically grab a reader to just read it into memory.
Because I'm wondering how can this hardware or can understand the TensorFlow description.
How does the hardware understand the description?
Right.
The hardware never gets the description. Basically, this is software. Okay, so this is software that reads in that TensorFlow frozen graph, which just means some data format that gives you a graph with annotations telling you what's going on. And then this software basically goes through a set of compilation steps in order to generate, in the end, an FPGA bit stream. Does that make sense? The hardware only knows I just do stuff. Okay, so the hardware is never given this graph. Does that make sense? Any more than your program, your C++ program that you actually run in an x86 or ARM processor, it never actually sees the C++ code that generated it, right? It is the realization of that input. Does that make sense? Okay, so there's some graph optimization. Resource allocation. So this is more important. So this architecture is called layer pipelined. We've got all the layers computing at once. Each of them is computing on a little bit of the input image, right? So we can't compute in parallel all of the data for the first layer of the CNN or the second. It would be too much hardware. So instead, with these processing elements that I talked about, if I go back here, this is working on a small part of the input image, and it's gradually scanning across it and producing output. And this PE is similarly working on a small part of the output that will come from the first layer. So it takes a large number of clock cycles to go through all of that input. Some of these layers have more work to do than others. So I showed you that some of those convolutions in that example network were 7 by 7 kernels. Okay, so that's like 49 multiplies and 48 accumulates to produce one output. Some of them were 3 by 3. That's 9 multiplies and 8 additions to compute an output. Some of them are stride 1, which means they compute an output for every input. Some of them have more strides, they skip over data. And also the sizes of the feature maps change as you go through a neural network. So you will find that the width and the height and the number of channels is gradually changing. So basically the amount of work that you have to do in each layer is different. And because it's a pipeline, we want to balance throughput. Whatever processing element that's working on a certain layer is the slowest, it's going to stall everybody else, right? Everybody else is going to wait for that. It'll start saying, I'm not ready, and everybody else will have to stall. So we want to balance the throughput. We want to allocate hardware to make whatever processing element is taking the longest go faster. And then finally, we generate RTL. And basically, that's done by, this tool doesn't try to create RTL for arbitrary things. It has essentially highly templated hardware for a bunch of different convolutions and max pooling and average pooling and so on, a bunch of things that occur in neural networks. And they're highly parameterized because it can change things like the kernel size, and it can change parallelism settings. So it can make bigger PEs or smaller PEs depending on how much throughput it needs. But that's where we generate RTL. It doesn't take something like a C description and try to generate hardware. It actually has these templates that are basically hand-designed, highly efficient hardware, but they're highly parameterized so that we can apply them to different layers, and we can get different amounts of throughput based on what parameters we send in. Does that make sense? And that's pretty common for these domain-specific compilers. Like underneath the hood, there's often a lot of highly optimized hand-generated code, but it's being parameterized and sent out by the tool. Okay, so that second stage of that compiler that I talked about was resource allocation. We have to balance the throughput of the pipeline. So this is an example for a neural network called ResNet 50. So it's got 50 layers. This is a pretty accurate CNN, but it has pretty high compute needs. Whoops, I accidentally went through the animation. So let's go back and see if we can see that again. Okay, so initially, if we use 712 DSP blocks, each DSP block in this particular chip can implement two 18 by 18 multipliers. We can implement all the layers, so we can build all the PEs we need. Turns out to be a little bit less than 50 because we've kind of merged a few layers. But some of these layers, their latency, which is like the opposite of throughput, is much higher than others. Okay, so some of these first layers over here are going really fast. Some of these later layers are going, more than 10 times slower. So if we just hook these up in a pipeline, this is what's going to determine our speed, right? It's the time to get through those later layers. Whoops, and this thing just keeps, every time I draw on the slides, it wants to keep going. Okay, so initially HPipe just makes every PE have the minimum parallelism settings, sees how much resources have I used, And if that's too much, we're in trouble. Okay, this architecture then would not work in that chip, but generally don't hit that. And then it starts allocating more resources to the slowest layers. So it's going to look at these ones out here and say, those are my problems, start allocating resources to them. So, and eventually this chip has 5,000 DSPs in it. It has increased the parallelism settings on the later layers, so the parameters passed into the final hardware generator, to the point where the latency of all of the layers is pretty close. And also pretty low, right? So like 0.2 or so of a millisecond, which means that if we put all this in a pipeline, we can get around 5,000 images going through it per second. So we get pretty high throughput. Okay, so that's like figuring out what the parameters are to balance the parallelism and get a good pipeline. Then we have to generate RTL. So I already mentioned this. So there's a template for every kind of layer that's been hand-coded by grad students, right, in RTL++. So what's RTL++? It's a Python-based library that one of the students developed. So he found that for highly parameterized code, where you got lots of inputs and you're changing how your hardware is generated, that it's difficult to do in System Verilog. System Verilog has some ability to write parameterized code, but he just found it was insufficient. So he went to one level above that of making a Python framework that basically knows how to connect hardware together and output System Verilog. And it gave him essentially more power in being able to change the hardware that comes out as a function of your input parameters. We instantiate every one of these layers uses the right parallelism parameters that came from that resource balancing stage. All of the interfaces are compatible, so they all use this latency insensitive streaming, ready, valid, with a FIFO buffer on my inputs style. So they use the same streaming style of communication, which means we can compose them. So we're composing a spatial pipeline using the streaming data flow model. And this latency insensitive design, so that's one of, again, that's that ready valid with FIFO's streaming style. It guarantees correctness. It means no matter whether the downstream logic is ready or not, so if there's basically some imbalances in throughput of these units, this is still going to make it all work. There'll be some stalls. Sometimes the hardware will stop, but it's guaranteed to work. So that's good. And we're using, because I kind of mentioned this before, we're using a coarse latency insensitive design flow. What that means is the FIFOs, the ready valid, it's only between the big blocks. So we have the FIFOs on the inputs to all of these blocks and ready valid signaling between them. But these blocks are pretty big. A lot of them have tens of thousands of logic elements, and inside each of these blocks, they just use regular pipeline registers. There's no ready valid signaling, because once the data has arrived here, we know what to do, okay? We can now compute maybe through the next 30 clock cycles, what do we need to do to produce a bunch of outputs, and there's no possibility that we'll have to stall or that we'll generate invalid data. So we use a very simple streaming model that can't be stalled inside of these blocks, and a more complicated one that can be stalled in between them, and lets us compose them all together. Make sense? Okay, so yeah, so each of these are all layers in the neural network. So this would be like a piece of the graph that defines a neural network. And this node in the graph, which is a conventional 2D convolution with a 7x7 kernel, we'd basically tell that RTL++ library that we wrote, I need this module. I need con2D, and I need it with these settings. And it'll go off and it'll make a .v file that does exactly that. So it will output the Verilog you need. Connect it up with the data, the valid, the ready, to the next module. So the next module is one that will implement this, and so on. The other thing that this domain-specific compiler does is it's pretty good at physical optimizations. So it not only outputs the RTL, that RTL is written to get very good performance on an FPGA. And we're going to talk about this later in the course, but basically, when you're designing FPGA circuits, you need certain blocks, you need certain RAMs. But those RAMs usually don't exist on the FPGA you have. So there's a process called RAM mapping, where you have to decide of these thousands of RAM blocks on the FPGA, how do you kind of combine them together to get the RAM your design needs? So H-Pipe does that actually itself. It doesn't rely on Cordis to do it. Cordis will do that for you, but H-Pipe decided that they could do a better job. So it decides exactly what physical RAMs it needs on the chip and puts that in. It thinks about the mux structure. So you get multiplexers when you start connecting these things together. And H-Pipe understands different ways you could make those muxes. So it optimizes that. And some of the, if I go way back here, there will be some long connections. Okay, so sometimes we'll have a layer that needs to feed another layer that's some moderate distance away. Also, some of these processing engines are getting reasonably large, so they can span a significant part of the chip. And when that happens, just the programmable routing can limit your speed. So H-Pipe doesn't just pipeline the logic, like the operations in the Verilog. It actually inserts additional pipe. What topology should it use to connect things? So let's say that I've got some source signal that needs to go to a bunch of destinations. A sort of straightforward way to do that is to build a tree. So the source goes to two registers, and those two registers now can be some certain distance apart. And then each of those goes to two of the destinations. So I got from one source to four destinations that might be pretty spread out, and I can do it fast because I not only put pipeline registers in, I basically kind of made a tree of registers so that I can put these two in different spots and localize my wiring. So it will do that when that looks like a good idea. Sometimes it also looks at, well, maybe I need to get to four destinations, and I can do it with less wiring if I make a linear structure. So I'll make four registers, so kind of a linear chain. All my wiring can be short. This actually means that when the data gets to these sinks, it doesn't get there at the same clock cycle. So then H-Pipe puts FIFOs in here to line the data up again. So this sink got the data 3 cycles earlier. So sink A got this data 3 cycles earlier than sink D. So with this style, this kind of chain of communication through registers, H-Pipe puts additional FIFOs or registers inside of these sinks to add more latency and line everything back up. And it turns out that sometimes that's more efficient. So it's kind of internally figured, based on its interconnect models, guessing which of these is more efficient. OK, so that allows it to run at high clock frequencies. So it hits, on Stratix 10, it'll usually hit 500 megahertz or so for most neural networks for something that fills the whole chip, which is pretty fast for FPGAs. And it gets high performance, so higher performance than any other FPGA accelerator that's been published to date. OK, so this is on a pretty big CNN called ResNet 50. It's pretty accurate, pretty resource intensive. And we're comparing to a big GPU. OK, so that GPU is actually in a similar process technology and has a bigger die size. So if you want low latency, so you're not using batching, you just get one image, you send it in, H-Pipe gets significantly higher throughput than the GPU can get. Okay, so if you give the GPU a big enough batch, so here we're grouping 8 images together before sending them into the GPU, which helps the GPU because it's able to bring weights on chip once and use them to work with 8 different inputs. It helps its throughput, but it still hasn't yet equaled H-Pipe, and its latency is now worse. Okay, so its latency's gone from kind of 1 millisecond to 2 milliseconds. Does that make sense? So it's basically, now if you keep extending this curve up to a high enough batch, it eventually does at some higher latency targets exceed the throughput of the FPGA accelerator. So FPGAs really like low latency. It's one of their strengths. OK, that was a conventional Stratix 10 FPGA. This is kind of getting ahead of ahead a bit. But a conventional FPGA has DSP blocks, which do they're optimized for multiplication, for basically signal processing for things like wireless communications. So Intel also has an AI optimized FPGA called Stratix 10NX. And basically all they change is they take the DSP blocks out and they put different blocks in. And we'll look at those ones later. They basically have more multiplications, but they're lower precision. So instead of having two 18-bit multipliers in every DSP block, you can get 30 8-bit multiplies in that same DSP, in what they call a tensor block. Okay, so you get more multiplications, but they're lower precision. And there's some restrictions on how you have to use them, okay, which I'm not going to get into right now. But basically, by changing that generator, that domain-specific compiler, to understand the restrictions of this architecture, we're able to use those tensor blocks well. And this is now on a different neural network, one that's also pretty accurate, but more targeted at resource efficiency. This is what HPipe gets on that AI-optimized FPGA. So it gets a very low latency, well under a millisecond, and it gets a high throughput of, you can, on one chip, do about 30,000 inputs per second. Comparing that to a comparable but actually somewhat bigger GPU is just better at every point. Okay, so the GPU can get more throughput if you give it a bigger batch, but its latency goes up. And even if you give it a very big batch, it can't equal the throughput of the FPGA, but its latency is much higher. So this architecture, works well for CNNs. Okay, does that make sense? So it's kind of a case study of, this is by no means the only such domain-specific compiler. There are a whole bunch, so you can go look up. If you're interested in this, there are a bunch of papers you can read. You can write your term paper on it. But this is one that gets quite good results versus GPUs. Any questions on that? Okay, so that's one approach. The other approach, make me a software layer that's going to automatically build very efficient processing engines for my input. The other approach is to make an overlay. And I'm going to give you an example of that called the Neural Processing Engine. And this work comes from work done by another one of my graduate students in concert with Intel to create an FPGA overlay targeting a different kind of neural network. So this overlay is targeting recurrent neural networks, so sequence processors that are used for things like language processing. So the overlay design flow, before we talk about the overlay design flow, let's talk about the traditional flow. The traditional flow of how you implement things on an FPGA is you've got one or more applications. You implement them in RTL. The RTL goes to the FPGA CAD tools. You see if it's meets timing, if it's fast enough, et cetera. If it isn't, you iterate. And when you're happy, you get a bit stream. Okay, so, and we just saw one of the ways to speed this up is, maybe we could make a CAD tool that understands how to make the RTL given an application in some domain. So that's the approach we just took before. What overlays do instead is they try to split out who's going to make an engine in the FPGA from who's going to use that engine. So you have hardware experts, so people who know how to make good hardware, how to get things out of FPGAs, who figure out what do we need in some domain of computation. So for the NPU, that domain is basically neural networks that process sequences, okay? LSTMs, RNNs, et cetera. They basically then develop two things. They develop an instruction set architecture, instructions that are going to control the hardware, and they develop a tool chain that can produce those instructions. So basically a software compiler somehow. It doesn't have to compile arbitrary software. For this particular example I'm going to show you, it just needs to understand sequence processing neural networks, but it has to be able to create instructions from those. Now those instructions have to run on something. So they run on an overlay. The overlay is the hardware engine that you put in the FPGA. And that hardware engine is built using this traditional flow. You write RTL, or you might write high-level synthesis. You run it through the CAD tools. You see if it's good enough. You iterate many times. So these hardware experts are doing two things: building a hardware engine using the traditional techniques, but then also producing, that hardware engine has some programmability that's exposed as instructions, so they have to define that instruction set and some way for you to make the instructions that's not too painful. Once they've done that, your application expert, so some machine learning expert, can basically just implement new neural networks in software. And what's called an overlay compiler, so the software tool chain that the overlay architects created, produces instructions, binary instructions that can be used to control the hardware. And that hardware is basically a bit stream that represents this overlay that was developed by the hardware experts. Okay, so does that make sense? So from the point of view of this application expert, they're just programming a somewhat unique processor. Okay, but if this, depending on how good this software tool chain is, they may not notice very much difference, or they might notice some of the difference, depending on how much the software tool chain isolates them from it. Does that make sense? I'm going to take that as yes, okay? So, I mean, one thing to watch for, though, here is you could say, well, I could short circuit this. I'm just going to use Neos or Microblaze or RISC-V. I'll just use like some conventional processor and use that as my soft processor. You could do that. Your performance will be terrible. Okay, your performance will be terrible because you're just using a regular processor, but you're also, so you're paying the overhead of all of the instruction overhead and the muxing overhead and going to the register files that a processor has, and you're paying all the overhead an FPGA has of making it out of programmable logic and routing. So it's not a very good solution. So the job of the overlay architect is to make something that's software programmable, but quite tuned to the application domain. Okay, and this application domain is not going to be like all C programs. If you said the application domain is all C programs, you just go buy a processor from Intel or AMD or ARM. Does that make sense? I think there was a question. Yeah. Yeah. No, so there's no general processor in here. Okay. The idea of this is this develop the overlay. This is still implemented in an FPGA. Okay, so you wrote HDL, or the overlay architect wrote HDL. It goes in the FPGA, but that hardware has some ability to be controlled by an instruction stream. So it is a usually very unusual processor. And that very unusual processor can be programmed, just using assembly language instructions, or if you've got a good software tool chain that can produce assembly language instructions from some higher level representation, then it could be programmed at a higher level. Does that make sense? Okay, so so that kind of what I showed you here is true of like all overlays. And you'll find there are a bunch of overlays for FPGAs that people have created, and it's an active area of research. So this particular one that I'm talking about, the neural processing unit, it's a very long instruction word soft processor. Okay, so it's combining a few of the data, a few of the compute models we talked about. So it's VLIW because it's got 5 stages, and you control each of them independently with part of your instruction word. So the instruction word is pretty big, and controls these 5 stages. You don't have to understand all the details of this. So again, this is an example. This thing is like multiple papers by itself. But for these kinds of neural networks, the most compute intense part of them is matrix vector multiplication. You're constantly multiplying your input activations times a matrix of weights and getting output activations. That's like the most fundamental operation in these neural networks. So there's a big matrix vector multiplication unit. It's highly parallel. Inside of it, it's got basically a couple of different register files. It's got a whole bunch of dot product engineer engines, because matrix vector multiplication can be thought of as a whole bunch of dot products being done together. And that's the biggest module, is this matrix vector multiply. Then it has a vector register file. So it also uses SIMD. So each instruction, each piece of an instruction, so there are 5 pieces of an instruction controlling these 5 units. Each one of them is not controlling like one operation on one piece of data. They're controlling operation on the whole vector of data. And the vectors are typically pretty big, 40, 80 elements, so it's quite wide SIMD. So that's the second level of kind of compute model they're using. So anyway, this is a vector register file. So it means you're accessing it. Let's say they made this NPU an 80 wide vector. Then you'd be accessing 80 registers in parallel. And then these are 2 function units. They're called multifunction units. They just do stuff you need in this kind of neural network. Addition, max, scale. So it basically has an instruction for everything. Each operation that you would need in this kind of neural network is inside one of these 2 function units. So they're kind of customized ALUs, and they also are operating with a lot of SIMD again, 40 or 80 elements at a time. And then there's some data movement. So there's a loader that basically figures out where do I put my partial result. Okay, so how does it get performance? Because I told you that there's a big overhead for FPGA soft logic. There's a big overhead for instructions. Well, these instructions are kind of weird, right? So it's SIMD, it's VLIW, and then the biggest thing is that the instructions that control this matrix vector unit are doing large operations. Like they're asking for entire parts of a matrix and a vector to be multiplied together, which is actually a lot of operations. So a single instruction can execute 45,000 operations. So that hugely reduces the overhead of instruction to code and figuring out what this means. You do have to do that, but then once you figured out what it is, it controls a huge number of operations. The memory subsystem that feeds this, which isn't really shown on here, is also very heavily customized. So instead of having a central pool of memory, the memory is distributed, feeding all the right units. So you can get huge amounts of memory bandwidth from the thousands of on-chip RAMs in the FPGA and keep all these units fed. Because 45,000 operations, launched by a single instruction, it's a lot. You're going to need a lot of memory bandwidth to keep that fed. It also customizes the data movement. You notice that this matrix vector unit feeds into this next unit, this vector register file, which then feeds into the next unit, this multifunction unit, and so on. So it's again specializing this processor. It turns out in all these neural networks, there's a sequence of operations that you tend to do. So instead of taking data and putting it back in memory or in some register file, and then having the next unit ask for it, they're just all chained together, right? So what comes out of this matrix vector unit just flows through the other units. And that's again to minimize data movement. Data movement costs a lot of hardware and costs a lot of energy. So you're trying to just, if you can directly send it to the next unit instead of looking it up from register file, you can be a lot more efficient. Okay, and I already talked about this. So it's targeting it's not targeting all neural networks. So it's not targeting CNNs, for example. It's customized to a certain sequence. Anyway, that was all the hardware. This is just a picture of like, how does this all work? This is all hand designed in RTL. Quartus gives you a bit stream for that. And then it can be programmed by basically writing in a domain-specific language that goes into a compiler. That compiler can just produce instructions so that without any more FPGA compiles, not going through Quartus again, you can actually change what neural network you're simulating or what neural network you're implementing. Okay, so how well does it work? So this is a comparison. It's again using this AI-optimized Intel FPGA, the one that has a whole bunch of 8-bit multiplications in it. And would like to compare things in the same process generation with around the same die size. So basically this V100 GPU is about the same process generation as the FPGA, and it's actually got a bigger die size. So the FPGA is at somewhat of a disadvantage. There's another GPU here from NVIDIA that's actually a little more comparable because its die size is closer. So anyway, this is showing normalized performance on a bunch of these, a bunch of benchmark neural networks. And on average, the FPGA is getting 11 times the performance of the big GPU and 23 times the performance of the GPU that is, kind of more of a comparable die size. So the results are good. Again, these are at low batch. So these are at batch 6. If you increase the batch size, the GPU gets closer, but it actually never catches up, and its latency is worse. This is another interesting result from this paper. So sequence length equals 8 and 256 are just different benchmarks. You know, basically, do I want to do a long sequence of inputs to my neural network or a short? So don't worry too much about that. This is showing that what you care about in the end isn't just compute performance. You also care about data transfer and the latency of that. So the yellow bars here are the time that it takes for compute. So smaller is better. And you can see the NPU bars are a lot smaller than the GPU bars. But they're smaller not just for compute, the yellow. They're also smaller for basically data transfer and setup. And the reason they're smaller for data transfer and setup is basically the FPGA is connected directly to Ethernet, and it can actually implement the Ethernet protocol in hardware. Okay, so it's got a low latency interface to the network. Turns out to outperform the PCIe drivers on the GPU. And it's able to essentially initialize the computation by just doing stuff like clearing block RAMs, again in hardware. And it saves time versus a GPU that needs to use some instructions to do all that. So this is something that not as many papers have looked at. They look usually at the core compute. But in this case, the FPGA is also benefiting from those kind of customized IOs and the ability to implement a communication protocol right in hardware. So they're getting additional latency advantages from that. Okay. Does that make sense? Yeah. Yeah. So these results are all made with one. So it's a good question. Okay, so let's just take the NPU. So for the NPU, there's a lot of investigation that went on both here and at Intel into how to make a good overlay. But then every result that I'm showing you here is with that same overlay. Okay, so these, yeah, all of these results come from one bit stream inside of the FPGA with just different software instructions. Does that make sense? There's follow-on work to this where Andrew, the PhD student who led this, showed that if you don't need to do all these workloads, so say you only need to do RNNs, you don't need to do some of these other variations of neural networks, you can actually rip out some of the hardware from the overlay and you can make it more efficient still. So it is possible to make more specific overlays that gain additional efficiency, or you can make a more generic one that doesn't require as many recompiles. So there's a trade-off space there. If you went to a totally different domain, like let's say you went to CNNs, which you didn't do here, then probably you want to change the overlay more. This particular overlay wouldn't be all that good for well, it can't actually do CNNs right now. Like it's just not in its instruction set. That's part of what you get by making an overlay that's customized to a domain. So if we wanted to go to a significantly different domain, you have to generalize the overlay or maybe just say we need a new overlay for that. That's why I don't think there'll ever be like there's one overlay architecture that's going to go in FPGAs because it's too generic. That overlay architecture will start degenerating towards something that's too close to a CPU or a GPU. And if you get too close to either of those, in my opinion, the extra programmability overhead you have makes it less interesting. There are still people who do that, right? I mean, so there are researchers out there making soft GPUs for FPGAs. So I'm giving you my own opinion that I don't think that makes, I don't think it's the best idea, right? But there are other people who disagree with me. I think you have to customize more to the application. Oh, can somebody reverse engineer your overlay architecture? Yeah, that's a good question. I mean, you can encrypt your bit stream. So you encrypt, so all modern FPGAs have encryption hardware, so you don't have to encrypt your bit stream. So if you're a grad student, you probably don't. You're just like, I don't care, right? The bit stream works. Why would I encrypt this thing? And some companies don't care either, right? They're like, I'm not worried about being reverse engineered, but some do, and they encrypt their bit stream. And the way it works is they actually, you get a code essentially when you buy FPGAs from your vendor, you tell them your encryption code. right? Or Quartus tells you this is your encryption code, and you tell that to the vendor, and they program that into the chip. Okay, so you get that encryption code, and your bit stream will work with those FPGAs that you're buying. If someone else buys an FPGA, even if they say, I want to use encrypted bit streams, they're going to get a different code, and your bit stream won't work with it. Now, if they can ever crack your bit stream, then they could say, I'll just buy an FPGA with no encryption on the bit stream, and it would work. But they have to basically break the encryption, which is possible. That has been done before. I don't know if it's actually harder now. I know for Stratix 3 and 4, there was a team of academics, there was a joint group between Germany and Iran who broke the bitstream encryption. They wrote a great paper on it. And they said part of what helped them is that in Quartus, we actually left all of the debugging information in so they could see what the names of the functions were. So they could actually see which ones were associated with encryption. That was actually a little embarrassing, right? They said this, they were confident they could have broken it without that, but they essentially like, hey, this is actually surprisingly helpful that software engineering did this. And since I was in charge of a reasonable part of software engineering, when I read that paper, I was like, we probably shouldn't have done that. Anyway, so they broke the encryption. Presumably it got hardened some more by the next generation, but I'd say it's hard to make an unbreakable bit stream. You're just kind of making it more difficult. Anyway, but that's a very good question. I know Cisco, for example, this is years ago, but Cisco was quite worried about this because there was a particular competitor where they were finding that they were just using all their IP, right? So like they were taking the whole software stack and just taking an image of it and shipping that as well. So they're pretty worried about them taking bit streams. So there are some companies that worry about this a lot, and there are other ones that don't worry about it much. Anyway, sorry, I don't know if I actually answered your question. I just kind of went off on a digression. Yeah, so you could try to sell the overlay. So that's a good question. So the overlay is essentially a really complicated IP core. And there are companies that do try to do that. So there's one that was a spin-off of University of British Columbia that makes customized vector processors for FPGAs. So there are a few like that. Yeah, so I think deep learning is probably a vector processor without further customization might still not be unique enough. Because I think one of your challenges with monetizing an overlay processor is you want it to be unique enough that it beats just an Intel or AMD processor that you could beat on some domain, but then you still want the domain to be big enough that you can make money. And I think there are some domains like that, like deep learning would be one of them. But anyway, that's a good question. Okay, so I guess final takeaways on this. Can FPGAs get good deep learning inference performance? So yeah, they can. So I just showed you results from HPipe and the NPU. And they use two different approaches, but they both get good performance. Can you make them easier? Yes. Again, using two different approaches, a domain-specific compiler or overlays. And there is a trade-off here. There's some tension between trying to make them easy to use versus trying to make them efficient. So these kind of hit different points. So you can also change the underlying FPGA architecture. So time permitting, we'll come back to this later in the course. This is kind of like, what do you do with the FPGA as a black box? But we're now moving into like the part of the course where we go into the FPGA and look at its architecture. And there's been a bunch of recent work about how can you improve the architecture of FPGAs or FPGA-like things for deep learning. So we'll come back and look at what are some of those ideas later in the course. But it makes more sense after you've looked at how do you actually architect an FPGA to come back to that. No, I'm not really talking about Grok, because Grok is different. Grok's not really, it's not an FPGA. There are a bunch of accelerators that vary from, this is an FPGA plus some stuff, to this is kind of like an FPGA, but different this way, to this is like a processor with maybe a few spatial aspects. Does that make sense? I would say Grok is more like a processor with some spatial aspects. So it's further from FPGAs. Something like Cerebrus is closer to FPGAs because it's got stronger spatial aspects. Does that make sense? And if you don't recognize those names, don't worry about it. So. Yeah. Okay, so that's it for those two things. I was going to do one more example. This example is related to the NPU. The NPU is actually inspired by and somewhat similar architecture to Microsoft Brainwave. So let's talk about this paper too. So it's a paper by Microsoft in 2018. It's another overlay. So it's related to the NPU that I talked about, but the paper has some interesting information in it. So I guess this is just data from Microsoft on how important is latency. So we talked about how it's important clearly in some embedded applications like self-driving cars or driver assistance. But Microsoft put really tight latency constraints on acceleration that's going in their data center. And they showed this graph in this paper. So Google, when it made its original TPU, how do people know what the TPU is, by the way? Have you heard of that? Okay, so TPU is basically a customized processor that Google made. It's an ASIC, but it's programmable because it is a processor. So it's also kind of related to the NPU overlay. It's not the same, but the key thing they did in their processor is they put a hard matrix multiplier in it. Okay, so a big chunk of the die size is this matrix multiplier that they can directly talk to with a limited number of instructions. So it's a processor, but an unusual processor targeting deep learning. Their first TPU paper, their target for latency was 10 milliseconds. Their second TPU paper, their target was 7 milliseconds. And Microsoft Brainwave, they target 4 milliseconds. So yeah, basically even in the data center, they're gradually pushing down on this because they want to be able to combine a whole bunch of deep learning models in a pipeline and still have a good response time. Microsoft also showed that at least in their data centers, that the bulk of the work is actually these sequence processors, RNNs, GRUs, et cetera. They're all things that do things like translation by translating one sequence to another sequence or figuring out what your search terms mean. And less of it was CNNs, that is more about image processing. That may not be true of embedded applications, because like driver assist and smart doorbells and so on, they're doing a lot of image capture. Let's see. So one of the key things they did here is they said they don't want to do batching because they want low latency. In order to avoid the bottleneck of going off chip all the time to get weights, which is going to limit their speed, no matter how many compute units they can throw at something, if they're always waiting for memory, that's going to bottleneck their speed. They basically said they want to get all the weights on chip. So that was their target. Let's see. So I already talked about this. Yeah, I guess they found that because they're targeting, they don't want to use batching because they want low latency, and they're targeting these sequence processors that are really built around matrix vector multiply. Instead of Google in their ASIC, the TPU, the core of it is a matrix multiply unit, a pretty big one. And Microsoft Brainwave and the NPU that I just showed you, instead, the core of them is a matrix vector multiply unit. Because they're not using batching and they're targeting these sequence processors. Okay, without batching, they can wind up with a big bottleneck trying to get weights from off-chip memory, because that's the problem that batching helps you with, right? Bring the weights in once, use them for like 10 images or 10 sequences, then get the next set of weights. So their solution to that is what they call persistent neural nets. If they can store all the weights on chip, then they don't have to worry about this off-chip memory bandwidth problem. Now then they could have a problem of, well, what if they don't fit, right? Somebody makes a big neural network that doesn't fit in one FPGA's memory. And to solve that, they pointed out that because they put these FPGAs in every node in their data center, they, in a sense, can be thought of as a giant FPGA connected by network connections. So they can split the weights across different FPGAs and count on the high bandwidth networking connections to just connect it all together. They can map a portion of the neural network to different FPGAs and have them all collaborate. So their compute model is, again, software programmable. It's an overlay. They actually have, okay, so they actually use NEOS, so a conventional soft processor, as essentially their control processor. Okay, so their compute model is soft processor plus a coprocessor. So the NPU, which is kind of related to this, is the compute model is like a custom processor using VLIW and SIMD and custom units. They basically say just a conventional processor because they don't want to reinvent the wheel for control, branching and so on. And they make all of the rest of it basically a giant coprocessor, like a coprocessor that is 1,000 times bigger than this Neos that is controlling it. And this coprocessor, like a single instruction, so the Neos writes to a particular register saying launch this operation, that can launch 7 million operations. So much like the NPU, a single instruction can launch a lot. Okay. I'm not going to go through this in detail. If you're interested, you can read the paper. But basically, I already talked about this for the NPU. Their architectures are quite similar of their compute units. You've got a big matrix vector unit, and you've got, let's see. Actually, I'm not going to circle all the various things because it'll take me too long, and I'll probably get one of them wrong. We've got a big matrix vector unit, and then some other vector units for less compute-intensive things. The other interesting thing they show in this paper is the impact of precision. So there are a lot of papers that show that neural networks are tolerant of low precision. So you don't need to use 32-bit floating point. People showed you could use 16-bit integers instead, then 8-bit integers. Sometimes even maybe below 8-bit it gets dodgy, right? So you may lose precision below 8, but at 8, if you do a good job of training, usually you don't lose precision. So what Microsoft is showing here, let's just look at the Stratix 10 line. They did this in 2 different FPGAs, so just look at the purple one. They're showing how much processing can they fit in terms of tera operations per second. So an operation is like a multiply or an add. How many can they fit in the chip? And if they do 16-bit int, they could fit 12 tera ops. If they cut that to 8-bit integers, they could do 31. So it's a pretty big gain. And then they started making custom formats that you can only make in FPGAs. So they did or in an ASIC. You could always make your own ASIC, but that's expensive. So they made a floating point, a 9-bit floating point, and they made an 8-bit floating point. And these don't correspond to any standards. They just put MS in front of them. They're Microsoft floating point. And if they go to the 8-bit floating point, they get like 90 tera ops per second, which is 7 times the performance that they got when they were just using 16-bit integers. Now, in neural nets, by doing this, they're cutting the precision. So they got to check, not only is it good for compute, but what happened to my precision? And here they've shown the results for 3 models. And the green bar is the MS 9-bit floating point, and the blue bar is the 16-bit. And basically, they basically equal the accuracy. Okay? They had to do a little bit of retraining. So it means if they get the red bars if they just take the 16-bit weights and they just kind of round them off. So they do lose some accuracy if they just do that. But if they go back through the training procedure and have it fine-tune the weights now that it knows there's some round off, they can get all that accuracy back. And these floating point representations they have are a bit unusual. So floating point is always like a mantissa. So it's like 1.01, for example, times some exponent, times 2 to the negative 8 or something. Like that would be what floating point really looks like. Some bits that represent the mantissa, and then some bits that represent the exponent. And they found that the exponent is much more important in deep learning than the mantissa. So not only is this like a small floating point where it's only got 8 bits, the mantissas are really small. So they usually wind up with 2 or 3 bits for the mantissa, and the rest are the exponent. It's kind of like the opposite of most normal floating point encodings. But by making that kind of custom encoding, they get good accuracy, and the hardware units become very small, so they get very good compute throughput too. Okay, and that is all I have to say about deep learning on FPGAs for now, at least. With time permitting, we'll come back to it when we get to towards the end of the FPGA architecture part of the course. Any questions on any of that? Was that, okay, I have a question. We'll see if anybody answers this. Was that the right speed? Because it's like always a question as an instructor, are you going like at a speed where people are going, I have no idea what this guy's talking about, or too fast or too slow. So is that the right speed? Okay, nobody thinks it's the right speed. Too fast. No, okay, too slow. All right, well, you can, you can tell me in the course of analysis if you're too scared. Or you can tell Amin and he'll tell me. I had one course with Dave Lewis, who then went on to architect many of Intel and Altera's FPGAs when I was a grad student many years ago. And he'd ask that question, am I going too fast, too slow, or just right? Everybody put up their hands saying too fast. Okay, so we weren't that shy, or maybe he was just going super fast. He would then slow down for the next 4 minutes, and then he'd go back to the same speed, right? So that's why I ask. Okay, let's take a 10-minute break. We'll start again at 5:27. Okay. papers. I gave you a bit of extra time, and I'll probably give you a little more than a week for these ones too. So 2 papers, and now we're kind of moving into the other part of the course, which is diving deep inside of an FPGA. So this first one is a survey paper written by myself and one of my PhD students. It's a relatively long paper, so for this reading, it's just read the first half of it, which talks about basically programmable routing, programmable logic blocks, and programmable I/O, and then we'll get to the rest of this paper later in the course. It's kind of an overview of important trends and things to consider in FPGA architecture and what's been happening commercially. The other paper that you can read is kind of how do you build a lot of the FPGA circuitry, well, programmable routing and the logic blocks in particular at the transistor level. And that's important because we're often trying to estimate, well, what's the speed and what's the delay, or what's the delay and what's the area of different choices for how we build these things. So this kind of goes through some transistor level design, so you hopefully have some feel for that. Okay, so I'll go back to my course concept map. So basically in the course so far, we've been kind of talking about why would I use FPGAs, how do I use them, what are these compute models, how do they compare to other devices, and then we went through some case studies of applications, like how do they fit into data centers, how do they fit into deep learning, and so on. And now, as denoted by the new color, we're shifting gears and going deep inside of them about how do you build them and what are some of the questions about how to build them well. Okay, so I'm going to kind of do an overview for the rest of this lecture of what's inside of an FPGA architecture. And then through most of the rest of the course, we're going to kind of dive deeper into various topics around that. Okay, so I think I'm going to just turn off the projector now. And let's see. Ooh, that's good. Can I stop sharing the screen? Sure. Okay, how's that? Okay, so PLD architecture. So we're going to start with what is in a programmable logic element. So the very first programmable logic elements were programmable read-only memories. And basically you've got n inputs. Those go through a decoder. So that produces, well, basically 2 to the n of these lines. Okay, so we detect we have a different value that turns on for any bit pattern that we put in here. That, let's see. Yeah, so we put a different value on one of these lines. Okay, so 2 to the n minus 1 of these transistors are not going to be on, and 1 will be. So let's say we put in the pattern, all ones. Maybe we've got 8 inputs, and we put in 8 ones. Okay, so then our highest order output is going to go high, right? So we've got 255 outputs then from this decoder. This is the only one that's going to be logic 1. All the other ones are going to be logic 0. So this transistor is going to be on. All of the other 255 rows, their pull-down transistor is going to be off. Okay, so this is the line we care about because it is trying to go to ground. And the way this makes programmable logic is we have fuses. And let me put this in. Okay, so the programming technology in these were fuses. So a fuse means it's initially connected. So it means this wire is connected to this wire. But I can destroy the fuse. I can blow it using some technique. Often it was like could be a higher current, could be something else. But I have some mechanism to program this device after fabrication by blowing the fuse. So this fuse has been blown. So this wire and this wire aren't connected. This wire and this wire still are connected. They have a pull-up. Okay, so this is an NMOS where the gate is connected to the drain. So basically, it's going to be permanently on. I've tied the gate high. So this is trying to pull this line to 1. But I make this transistor smaller and weaker than this transistor. So if this is still connected, this line and this line are still connected, then this guy's going to, let me think about that for a second. Okay, so actually I need to make this one stronger. So I make this one stronger. So if these are still connected, this guy's going to get pulled up. And if they're disconnected though, let me think about that. No, I want to go back to my initial one, okay? I make this one the stronger one. Sorry, I've confused myself. Yeah, I make this one stronger. If they're still connected, this guy wins, and it gets pulled down to 0. If they're not connected, then, well, this guy wins by default, right? There's nothing else, so it's going to go to 1. Does that make sense? So by choosing what bits to blow, I can basically have any function I want of all my inputs. Okay? Any bit pattern I put in my inputs is going to activate a different row, basically. And then depending on whether or not I blew a fuse, if I didn't blow the fuse, I'm going to get a logic 0. If I did blow it, I'm going to get a 1. Okay? So that means if I have m outputs and n inputs, I can do any function of my n inputs. And actually not just one function, I can do m functions because I have m outputs of my n inputs. Does that make sense? And hopefully you get the circuitry. I confused myself as I was doing this, but now I have notes. So I've recaptured which is a 1 and a 0, hopefully with me. Okay, so this is a weak pull-up. Okay, meaning that it will lose if it's fighting this. Okay, and you make it a weak pull-up by doing things like, well, making it minimum width and maybe making its channel extra long. So this is not a hard question. So what is the area? Okay, how does the area of this scale with n and m? And I'm not looking for a really detailed model here, so this is not like a super hard question. As I change the number of inputs, how does the area change of this? So go ahead, say it loud. Sorry, I couldn't quite hear you. So. Exponential, yeah. So with inputs, basically the size of this decoder, like a number of its outputs, is going to grow exponentially. Okay, so with number of inputs, it's going to grow with 2 to the n. What about with number of outputs? What do you think? It's linear, so number of outputs is not as bad. But this is pretty big. Okay, so it's okay for a small amount of logic, but you can't scale this to really big amounts of logic by changing, well, m's not too bad, but if you want to start changing n, it gets ridiculous after a certain size of n. So we can't make this really big. Okay, so it's useful, but it's not very scalable. Okay, and then I've actually drawn the second thing that people came up with. So the second thing people came up with, they confusingly came up with two very similar names for slight tweaks on this, but programmable array logic or programmable logic arrays. They both basically look like this. You have a bunch of inputs. You complement the inputs, so you get both the true and the complement form of the inputs available. You have a bunch of programmable switches that allow you to connect any set of these to AND gates. Okay, so here I would actually need to have, this would be a 5-input AND gate for what I've shown. If I had just 2 inputs, well, I need to have 5, and I have 1 feedback. Okay, so I have 5 little X's here, which means this actually has to be a 5-input AND gate. I just didn't draw it that way, I drew it in a simpler way. And I have another 5-input AND gate down here, and I can choose to, by programming these switches, connect or not connect various inputs of their complements to my AND gates. I have some number of these AND gates. Here I've taken 2, and they go into an OR gate. And that knows 2-level logic, right? So you can do anything with a combination of AND and OR. That wouldn't be enough to do sequential logic. So by this point, people want to do sequential logic too. So you put a flip-flop in, a multiplexer that you can also program to allow you to do that. And you have this ability to feed signals back so that you can do sequential logic, or maybe you just found you needed to do, your logic was complicated enough that you needed to do maybe a 5-input AND and then feed it back, and then in another one of these, what is called a macro cell, you might do some more ANDing. So feeding this back is useful for sequential logic. It's also useful if you've just got really complicated combinational functions. You can kind of make you can pass through one of these, and there's another one down here. You could pass through another one to do some more ANDing and some more ORing. So does that make sense? So you can also do anything with this if you have enough AND and OR gates, because you're basically implementing two-level logic, which you learned probably in second year, that if you do a two-level logic and you have big enough gates, you can kind of do everything, or you can just keep cascading two-level logic over and over again, and you can do anything. What's the area of this? Maybe this is a bit harder. What's the area of this proportional to? I've only given you two variables, inputs and outputs, right? So it's going to be a function of inputs and outputs. That's the level of detail we're going for. So if I add more inputs, what happens? So I told you right now this is a 5-input AND. If I added one more input, and I'm going to get its complement as well, will this still be a 5-input AND? What do you think? So it's not going to be a 5-input AND. I would wind up connecting. If I put one more input in, I'd basically go, well, here's another input. I'd put another set of programmable switches in, and this would go from a 5-input AND to a 7-input AND. So basically, my area is going to grow linearly with the number of inputs. Okay, so it's proportional to inputs. Because if you count up the transistors and the AND gates, they'll go up linearly. If you count up the programmable switches, which also matters, that's also going to go up linearly. Okay, now what about outputs? So to get more outputs, I basically replicate this whole thing. Okay, I just say, okay, I got more AND gates, more programmable switches to connect to my inputs, another OR gate, more of this. You know, if I want another output, I just duplicate this whole thing. So how is this going to grow with outputs? This is going to be linear, right? So it's inputs times outputs. It's actually better than that. Although to do a sufficiently complicated function, I might have to go through this, you know, use these feedbacks to kind of go through multiple times. But it grows better than my programmable read-only memory. But it's still not very scalable either. So what I mean by not very scalable is if I go, well, nowadays on a chip, you know, I could have functions that have huge numbers of inputs, right? 256, 512, and I could have 1,000 outputs because I'm trying to build some complicated circuit. Well, that's going to get pretty big, right? So it's not very scalable to very large sizes. Okay, so next thing that came out was the lookup table, or LUT, which was in 1984. Okay. So there's a patent on this. Who do you think patented this? Wasn't me, right? I was only, I was like 14. Okay, so it was, I didn't have a patent on it. So who do you think patented this? It's probably like, if you guess, there's some logical guesses. This is not one of those weird ones of like, it wasn't Barack Obama or something, okay? So there are only a limited number of guesses that you might be able to do. What do you think? You don't need the name, just like what company patented it? What's that? Xilinx, yeah, this was Xilinx. Okay, so this is a really valuable patent. It's called the Friedman patent. It was one of their founding engineers. I worked for many years at Altera. This patent is really annoying, right? So there are some patents that are like really valuable. That was a really valuable patent. So, but it's now, patents only last for like 20 years. So this is expired, so you can go out and make your own FPGA company, and you can happily use the lookup table. So it's kind of building on this idea. You know, it is a form of read-only memory, so it is related to that. And we already talked about this. So it's basically an SRAM. And you follow the SRAM with a multiplexer. Okay, so this might be the 0, 0 data item. This might be the 1, 1 data item. Okay, I hook my inputs up here. That's not going to do, this will only do combinational logic. So if I want to do sequential logic, I have to put a flip-flop in as well. But I might not always want to go through the flip-flop, so I bypass it with a mux. Okay, put an SRAM cell to control whether I do that or not, whether I use the register or not, and I have an output. Okay, so we kind of did this before, but let's just make sure everybody's with me. Okay, so let's say I want to make this function. Output is equal to input 1 exclusive OR input 2. So I'm going to program my SRAM cells. That's where I get the programmability now. These, this one was using fuses. This one was using programmable switches. This logic element, you just program in SRAM to make it do what you want. So what do I put in? Okay, so this is the 0, 0 value. When I put in input, the XOR of the two inputs. You only got two choices. So it's like you're 50-50. Even if you have no idea, you're like, I don't remember second year, right? You still got a 50-50 shot. So it's the beauty of Boolean logic. So you can go back, if you ever go back and visit your second year digital logic teacher, you can just say, how can anyone fail this course? If you just guess randomly, you should get 50%, right? So your 241 instructor probably won't like that comment, so don't say that. What do you think? What should I put here? Right, so that's 0. What do I put there? 1. Right, and then here, 1 and 0. So so this function is nice. One of the nice things about this is it can do any, it's kind of back to this style. It can do any function. This structure can kind of do some functions, if they can be decomposed into 5 input ANDs and no more than 2 inputs to an OR. So that does some functions with a certain number of inputs, but not other ones. This one can do any function as long as it has fewer than k inputs. Here, k equals 2. So k is just the number of inputs. So that's nice. How does its area grow? So what's going to dominate in the area here? So some area to this mux, some area to this flip-flop, some area to this mux, some SRAM cells. As I change, okay, so there's only one output. Okay, so the ECE is only going to vary with inputs. How is it going to vary with inputs? What do you think? Linear, square, factorial? What do you think? Right, so it's going to be, and we usually, it could be n, but we usually just use k. I'm going to use k for the number of inputs because it's just more conventional in the literature. So the area is proportional to 2 to the k. Okay, it's because, well, the number of SRAM cells increases exponentially as you add more inputs. If you actually go inside this mux, which we will do next class, you'll also find that it also grows exponentially. Like when you look at all the transistors you need to build it, this mux also gets bigger exponentially in k. Okay, so basically this is also not scalable. So I'm saying not scalable, it doesn't mean bad. It's just one of the things you can think of is like, well, can I just make a logic element and then as you get more and more transistors, you just make it bigger and bigger. And we're done, right? Like that's the best programmable logic you can get. So far, that's not true for any of these. They kind of are reasonable as long as you keep your number of inputs and outputs reasonable, but if you make them grow sufficiently large, they kind of become absurd. And this one becomes absurd faster than most, right? You can't make that number of inputs very big. Okay, last logic element that is in, well, there's one more I'll show you on the screen, but this last one that's kind of commonly used is mux-based. And that's used in some of the devices by Actel which is now part of microchip. Okay, so what does this one look like? It's related to the lookup table. So you're going to see there's some commonality to it. Okay, so okay. Okay, so it's kind of like a lookup table, because this is actually a 4-to-1 mux, which is what I've got in that lookup table there. But instead of connecting the inputs, well, we do connect the select inputs of the muxes to, just inputs to the logic element. But instead of connecting the data inputs of the muxes to SRAM, we just connect them to other inputs to the logic cell. So we could have I1, I2, I3, I4, I5, I6, and I7. Okay? Okay, so it kind of has parts of a lookup table in it, but it's also got more. And the other thing that's important to know is, so I can connect these inputs to just some signal, but they also can be connected to power or ground. So they build the programmable switching to bring signals in. This could be something coming from the programmable routing, or power or ground. And you do that just by having a few more programmable switches. And that's true of each one of these, okay? Turns out that that's important, right? If I can't connect it to power and ground, this might be difficult. But I can basically make these inputs power or ground if I want. Okay, so let's say I want to make this function. Okay, A exclusive OR, B exclusive OR, C. So we're up to a 3-input function now. How would I map this? So you've got A, B, and C. You got power and ground. You can connect those to any of these inputs you like. So and I'll tell you that, well, do you think you can do this? Can you do this function that is a 3-input XOR? What do you think? That one you just take a guess. Okay, so I see somebody guessing yes. That sounds good. So I'm not going to put you on the spot by saying what is it. Can anybody tell me what the mapping is? There's not only one, but there are multiple ways to do this. Can you come up with any mapping of A, B, C, power, and ground to this so that the function that comes out is this 3-input XOR? What do you think?
For I1, I2,
Okay, so for I1 and I2, you want A on one and B on the other? Is that right? Okay, and then what else do you want?
and lower side, I also put A and B.
Also A and B? Like that? Okay, and then what do you want for the other ones?
For the selector, I put like 1 and 0, like
You want 1 here and 0 on here? You're going to have to use C eventually, right? Because otherwise you have an oracle logic element. It's unconnected to like the final input, but it just understands it. So that would be magic. So what do you want C here?
C, I put C on the I6 and I5.
Okay, put C on both of these. All right. And then what do you put on the last one here? What do you think? I'm going to give you a lifeline if you get stuck. So you can call a friend if you want. You want to call a friend? So you can pick anybody here and just say, OK, I'm going to call a friend. What do you think? Do you want me to call a friend? Can I call you as a friend? Or do you want to do ask the audience? You want to call Amin? That's not a bad choice, right? OK, we'll do ask the audience lifeline. So I think you're not quite sure what to put here. So it's the right idea, but I don't think it's quite working yet. We can just walk through it. Let's say A is 1 and C is 1. Okay, so then I'd get, well, let's say C is 0 and A is 1. Okay, So then I would get a 1 flowing through to this point, and I'm not quite sure what to do. Okay, but in that case, it would be fine, even if I said I could tie 0 to here. Okay, so that case works. If B is 1, and if A is 0, and C is 0, it works again. Okay, does that make sense? Although I didn't use B at all. That's actually a bit weird. So it's a bit odd that because I could also break this by doing B. So it's not quite working. Okay, so I guess I got A, the correct value for A if B was 0, but the correct output value for this path if B was 0, but not if B was 1. And there's just kind of no mention of B along here. Does that make sense? That's probably a hint of like, probably any path from input to output, I probably have to somehow have some, it has to look at A, B, and C, because otherwise that path has no knowledge of all 3 inputs. Does that make sense? So anybody else want to take a shot at this? Yeah.
So you connect A to I1,
Okay.
A naught to I2,
Okay, so we can change this one to A naught. Okay.
and then the same for I3 and I4.
Do you want A on this one and A naught on this one?
Yes.
Okay.
And then for I6 we do B, and for I5 we do B naught,
Okay, to B here, B naught.
and for I7 we do C.
Okay, and then we'll do C. It's looking pretty good. Okay. Oh, and this is another thing I should say is that, yeah, you can connect the complements. If you can't, you can generate the complements in other logic cells. If you can't generate the complements, this becomes kind of impossible, actually. So if you were trying to do it without complements, you were solving a difficult and probably insoluble problem. So sorry about that. Okay, so if A is 1 and B is 0, then I'm going to go through this path, and C is 0, I'm going to get a 1. So that sounds good. If A was 0, then I would get a 0. So that sounds pretty good. Let's say B was 1 and C is 0, then I'm going to get this path. If A is also 1, then I will get a 0. If A is 0, I will get a 1. So that looks good. And if I go through this one, I think it's going to work too. So let's see. If B is 1, I'll get this path. And if A is 1, then I will, and C is 1, then I'll get a 1. So that sounds good. And if A is 0, I'll get a 0. So yeah, this looks good. Okay? And the last one by symmetry I think works out. I'm not going to do it. So it works. Can I do a 3-input XOR in that 2-input lookup table? So this is a 4-to-1 mux, by the way. Right? That's actually how you build a 4-to-1 mux, sort of a cascade of 2-to-1s. So I've kind of got part of that lookup table. But instead of SRAM cells, I've got just signals connected to the input here. Can that 2-input lookup table do a 3-input XOR? Is there any way to do that? What do you think? Anybody think it can be done? Anybody think it can't be done? Yeah, can't be done. Why can't it be done?
Because you only have 2 inputs.
Yeah, it just doesn't have enough inputs. There's nothing else you can do. So this can fundamentally do any function of 2 inputs, and it can do 0 functions of 3. Okay, so can't do this. This can do 3 inputs. Can this also do any function? Can this do everything that that lookup table could do? Like, is there any function this can't do that the lookup table can do? What do you think? What function would it be? Because I can put 0 and 1 here if I want. Like, I can connect these to power and ground. Does that make sense? And I can connect both of these to, say, input 1 and this one to input 2. And now I've basically built a lookup table. So this actually can do everything that that lookup table can do as well. So it sounds better. Okay, so basically, maybe a way to capture that is a positive of this is that the area of this is actually proportional to the number of inputs. So if you kind of look at how much it takes to build these multiplexers, this is going to scale. If I added one more level of multiplexing, I'd get twice as many inputs. Okay, and I would need about twice as much circuitry. So the area of this actually scales pretty well. Area is proportional to the number of inputs. And it can do everything that lookup table can do, and it can do some things it can't. So is there anything bad about this one? Because this is used, but lookup tables are used even more. So why would that be?
Functions are difficult to map.
Yeah, the mapping is more difficult, so you have to think a little more about this. Although you can make CAD tools that, a classic thing in the FPGA industry is the hardware people just do whatever they want. Well, it depends on the company. Like the more sophisticated, mature companies, they don't do this. But startups, they have their hardware engineers just do whatever they want, and then they just assume software can solve it. And that isn't always true, but it is a widespread assumption. So let's just say I buy into that and I go, yeah, software people will solve that. And they probably will. Yeah.
So as we increase the input, the number of inputs, like the wiring,
Yeah. Yeah, so basically if we only look at the logic cell itself and we just assume getting all these inputs there, right, like this would actually probably be the best thing. But the negative of this is all these inputs are important. So it's basically got more, what I'll call routing ports. Okay, so every one of these inputs isn't just a piece of wire, which even in an ASIC is a bit of a problem to have lots of inputs. To get an input here, we need programmable routing. And we're going to see in a little while, like, what does that mean? It means prefabricated wires with inverters driving them, and more importantly, multiplexers and SRAM cells to control those multiplexers to switch between them. So these are pretty expensive. And we'll figure out kind of some bounds on that. But just, yeah, so the expense is the fact that we have more inputs. In order to make use of the extra power of this mux, we need to allow more different ways to hook up the inputs, and that's actually a big deal. So more routing ports, which is expensive. And I guess related to that is it can't implement most functions with all the inputs used. So usually if the number of variables in your function is equal to the number of inputs, this probably won't be able to do it. Okay, so this actually has 7 inputs, and it can't do very many 7-input functions. It can do multiplexing, but not very many other, like it could do a 7-input mux, it could do a 4-to-1 mux, which is a useful function, but there aren't that many other 7-input functions that it can actually do. So that would be fine, except for the fact that these inputs are expensive. So if you hook all those inputs up, you want to get a lot of value for them. So this one's also, kind of also not, it's a reasonable one, but it's not scalable either. It's kind of more scalable. As you make it bigger, its area doesn't grow as quickly. But because of the cost of the routing ports, you wouldn't want to make this all that big either. So, okay, so what does this mean? So we have nothing where we can just kind of say, let's make huge logic elements. So we're going to make moderate-sized logic elements, and we're going to have to combine them. So we have to combine them with programmable routing. So we need routing networks. So that's the second big part of an FPGA. Okay, and there are kind of two main types. So the first kind is called a hierarchical network. Okay, so here's an example of a relatively simple device that uses that. Okay, this is a device that Altera makes, and they've sold a huge number of them. It was some years ago they'd sold more than 50 million of these. Now it's probably a lot more than that. Okay, so they basically make this structure, right? This and/or structure, and this scales up to some reasonable number, maybe 32 inputs and 32 outputs. It'll scale up to a reasonably high number of inputs and outputs. But beyond that, this quadratic growth starts getting you. So to make a bigger programmable logic device like that, they basically just said, okay, can't make the inputs and outputs much bigger. It's too costly. So we'll just make a bunch of these on one chip. Okay? And then in between, we're going to put a switch network to allow their inputs and outputs to connect to each other. So it kind of behaves like a single bigger. programmable logic device. Okay, so we've got some outputs that go into the switch networks. We've got some inputs that come from the switch network. All these things can now talk to each other through this. And so this is how all programmable logic is designed now. So you basically, you make some logic blocks. So these would be a form of a logic block. In this case, they're this inside. And you group those smaller logic blocks with some kind of switch network. Okay, so the easiest switch network that I can think of is, let's make a crossbar. Okay, so a crossbar allows me to connect any input of the switch, or any output from the switch network, which would basically be something going into one of these PALs, to any input. Okay, so some signal that went into the switch network. Okay, so we could use a full crossbar. So full crossbar, yeah, if you haven't heard that term, it means any output can be connected to any input. There's no restrictions, no blocking. It's like the kind of nicest switch network you could ever have from that point of view. But what is its area? How does the area of a crossbar grow? Any idea? There are a couple different ways you can build these, but they both grow with the same area asymptote. Yeah, it's n squared. Basically, they grow as inputs times outputs, which if they're both n would be n squared. So, I mean, it's not too hard to see why. Like, one of the ways that these are built or can be built is you basically make a wire for every output, okay? And you make a wire in the other direction for every input, and you put some kind of programmable switch wherever they cross. And you can pretty quickly see, well, the number of programmable switches is like n squared. You can also build them with multiplexers instead. If you build them with multiplexers, you wind up with one multiplexer for every output, and the number of inputs is equal to the number of inputs to the whole crossbar. That actually also grows as inputs times outputs. So either way, you get this behavior. So this is also going to limit us, right? So we did this because we had this growth in this structure of inputs times outputs. So we're trying to defeat that. If we use a full crossbar, we wind up with, well, the growth is still inputs times outputs to the switch network. So we're not really much better off. So you can use full crossbars as long as they're not too big, but you can't just keep scaling a chip up and just saying we'll use a bigger and bigger full crossbar. It becomes, well, the area growth, again, is untenable. So what they do instead is they use some kind of complicated multi-stage routing network. And if you do that, and we're going to talk about that a bunch. So if you're kind of going, what do you mean by complicated multi-stage? Yeah, it means more complicated than a crossbar. You have to go through multiple levels of switching. You might get blocked. You can't always connect every input to every output. But if you do that and you do it cleverly, you wind up with an area that is proportional to inputs plus outputs. Okay, and this is a big part of making a good FPGA architecture is exactly what does that mean, right? There are a lot of different ways you can make some complicated multi-stage routing network. If you do it well, the area is pretty good and it doesn't block that often, meaning you don't get routing failures very often. If you do it poorly, the area is big and you get lots of routing failures. If you're a startup, you then go get mad at the software people. They get mad at the hardware people. And there's lots of blame that occurs of who made the mistake. But it's not a good situation. Okay, so I'm going to erase this and we'll, or actually I might still have boards left. Let's see. Aha. Okay, so let me draw what one of these multi-level ones would look like. So this is basically like a one level of hierarchy. or maybe 2 levels. I've got logic blocks, and then they have a switch network between them. And this switch network, as long as the number of inputs and outputs aren't too big, so I've got 4 of these blocks, maybe that's okay, I can make a crossbar. And in fact, this chip did just use a crossbar. Okay, so it works when you just got 4 things connected to it. But if you made this into 16 things connected to it, the number of inputs and outputs starts getting unwieldy. So to go to bigger chips, hierarchical FPGAs have to go multi-level. Okay, so let's see if I can, I'm organizing how to draw this. Okay, so I've got a logic block here. Okay, so say I've got 2 logic blocks. I want to be able to programmably connect them. Let's say they each have 1 output. So I just make 2 routing wires, and I make programmable switches that let me connect the input and output of this block and the input and output of this block to those wires. And my CAD tools can figure out which switches to turn on, so these things can talk to each other no matter what. Probably I'd have more than 1 input and 1 output, but I'm just keeping it simple. Okay, so I only need a couple of wires. So that connects 2 logic blocks. If I want to make a bigger chip, I repeat this structure. So I make 2 more logic blocks down here. Those logic blocks need to be able to talk to each other, so I make 2 more routing wires. I put switches there. How much is this blocking people, by the way? Can you actually see what I'm writing, or should I move to a different board? This is kind of an annoying one. What do you think? Who can see this and who can't? You can kind of see it? All right, I'm going to keep going then. Sorry about that. I'll try to watch this dead zone. All right, so now these guys can talk to each other. And then I put some wires in between. Okay, so we call these a level 1 wire. Okay, because it connects these 2 guys. And these are also level 1 wires down here. And I'm going to make some more programmable switches. And we'll call these level 2 wires. Okay. If I want to do more, I just repeat this whole structure again. Okay, so I'm not going to draw that whole thing, but pretend I drew these 4 logic blocks again with all of this local routing amongst them. And then I'm going to basically connect them with some even higher level wires. Okay, so maybe I do that, that, and I'm making my switch pattern sparse. So I'm not connecting every level 2 wire to every level 1 wire and so on, because you usually don't need that. So to kind of have the area grow more slowly, I'm using sparse patterns of switches, and my CAD tools are going to have to figure out, can they connect it or not? And this will be one of the things I got to figure out when I'm making the chip, of how sparse can I make these switches and it's still okay. So these ones now are the level 3 wires. Okay, so okay, this is actually used in quite a few chips. Has been used in quite a few. So there's an academic paper called High-Speed Reconfigurable Array. This was used in Altera's Apex chips and their 10K chips. And it's used by a company called FlexLogic that makes embedded FPGAs. Okay, so embedded FPGAs are FPGAs you can buy as an IP block, and you can embed them into an ASIC if you're making some larger system on a chip. So what's good and bad about this? So what do you think? Is there anything you like about this, anything you don't like about this? I have a few positives and negatives on this kind of architecture. Any ideas? What do you think? Yeah.
But if you have too many crossovers, this will start to perform fairly poorly because of how many routing levels it is having to jump.
Yes, that's a good answer. So I'm going to break that down into a couple different things. Okay, so a positive of this, and kind of the reason this exists, is it matches the hierarchical nature of designs. So hardware designs are generally hierarchical. So what do I mean by that? Like let's say you're writing HDL, and it doesn't actually matter if you wrote this yourself or used a high-level synthesis tool or some domain-specific compiler, because they make HDL that looks a lot like what humans write anyway. So at some point it turns into HDL, and you might have something like a module C1 and a module C2 that you instantiate, and they're both instantiated inside some higher-level module C3. Okay, so I mean that's how HDL works. Like a module C3 instantiated this submodule and this submodule. If I go inside these, they might have submodules and so on. It's fundamentally hierarchical. And what happens is normally you'll have some connectivity between these. So these will be hooked up with some signals, but the number of signals going between them is usually less than the number of signals that are inside of them. Some of the signals inside here will just be local, and they don't make it to the ports. And that's true at kind of every level of hierarchy of your design. Some of the signals don't make it up to the next level of hierarchy. They're not important enough. They were local communication. So we're exploiting that in this architecture by we're not building as many wires as we go up. So at this level of hierarchy, we have 2 wires here and 2 wires here. So 4 total wires. But when we go to the next level, we only have 3. Okay? And if I was to now compare the number at this level compared to the number of level 3 wires, well, I have 3 wires here, and I have 3 wires in my mirror image here at level 2, so that's 6, and then I only built 4 going between those big blocks. So I'm building fewer wires as I go kind of higher and higher up in the design hierarchy or the physical hierarchy, and that matches what happens normally in a hardware design, is as you go up the hierarchy level, there are fewer signals crossing between modules. Does that make sense? I mean, there's more total signals. You can have wide buses between C1 and C2, but there were some local signals that just didn't escape from here. So you need fewer signals between these 2 modules than the sum total of all the wires inside this one plus all the wires inside that one. Does that make sense? And that helps this scale to bigger sizes. Okay, so we can actually analyze that. So let's see, to write that more formally. So the number of wires at level I is less than the sum over all of the channels of the wires at level I minus 1, the lower level. Okay, which is what I just did with a couple of examples over here. That's just writing the general formula of that. Why is that good? It helps scalability. if we want to make a chip twice as big, we have to duplicate everything we had at this level of hierarchy over here, so it's twice as much area. And then we have to add some more. We have to add these wires between them. But the number of wires we add here is less than the sum total of the wires we had in these two blocks. So it means it's going to cost us some, but it's not going to be as bad. Okay, so this can actually be analyzed as well. So there's a rule called Rent's rule. Okay, I'm pretty sure no one will have heard of that because you haven't taken Jason Anderson's course because he's on sabbatical. Okay, so Rent's rule is something that was noticed by an engineer at IBM many years ago initially for circuit boards, when they're actually putting discrete components on circuit boards, but it's been found to be true for not just circuit boards, but also inside chips. And that's where it's more used now, because there's more complexity inside chips. Okay, so it's a rule that's just, he empirically observed it, is the number of terminals, so the number of things going in, number of inputs plus outputs, basically, things going in and out of some component is equal to some constant times basically the amount of logic in that component, so the gates, to some exponent p, okay? So this rule just relates how much stuff is in some module, how much logic, how much compute, how many gates. How does that relate to the number of inputs and outputs to that module? And yeah, this rule has been found to hold for a whole lot of different technologies. So let's see, I'm going to erase this. Okay, terminals and basically amount of logic inside. And this P thing. So this P is a parameter that's called the Rent exponent. I already told you this, but T is equal to the number of terminals. So the useful thing about this P is that it's always between 0 and 1. Okay? So it is always less than 1. And so different kinds of circuitry have different Rent exponents. This is a measure of how local the communication is. If your Rent exponent is very small, you have a lot of local communication, not much global communication, which is actually good when you're trying to make an efficient chip where you don't use much interconnect. If your Rent exponent is high, you have a lot of long-distance global communication, which is harder when you're trying to make a chip. And different designs have different Rent exponents, so it's not like one of these is always right. So let's do examples of what would be kind of recognizable designs and what the Rent exponents are. So if P is equal to 0, all right, well, gates to the 0 is just 1. So it means that my terminal count is constant no matter how much logic I put inside my system. So I keep putting more and more stuff in this chip, and the number of IOs at the top level just don't change. So can you think of anything that would do that? Like, is there some, can you think of any system where you just put more logic in, more processing, and the number of inputs and outputs doesn't change? Yeah. Well, I guess a LUT does change. The number of inputs changes if you make a bigger LUT. It changes slowly, but it will change. So this might be a hard question, because it might be, without seeing what I'm thinking about, you might not be able to kind of guess what I'm talking about. But P equals 0 is kind of the best locality you ever get. So terminal count is constant. And it's basically an example of this would be a chain of blocks. So let's say where let's say I'm doing signal processing. And let's say I'm adding more and more filters, but just on the same data, right? I used to do one filter on my data, now I do two. Then I decide, well, I'd like to do some more processing. I'll add two more signal processing blocks, but their inputs are always just the same data. So I start off with, one module, and let's say I've just got one input and one output. So number of terminals to this is 2, one input and one output. And the amount of gates is whatever it is, right? It's like one compute unit. If I decide that I can do, I have a long pipeline of signal processing operations to do, so I find I can fit more of them on my chip. So I add one more block in the pipeline. Okay, so this was my first thing. Now I can fit more. This is the next level of hierarchy. Number of terminals is still 2, even though I have twice as much processing. And I can just keep doing this, right? So I add another level of hierarchy where I put 2 of those, 2 more blocks in. And if I draw a box around that, the number of terminals is still 2. Okay, so T equals 2, always. And systems like this exist, right? Where you're just kind of increasing the amount of computation, but in a linear pipeline. So your routing is very local. Like, it also makes sense if you think of what's happening, of how far your wires have to go. They only have to go to the nearest neighbor. Your wires are all short. Your terminal count's not increasing. This would be a really nice circuit to lay out. Okay, let's see. Erase this. So can you think of something that's going to have a rent exponent of 0.5? I'm going to erase this board, and you can think about that. So, yeah.
And for the default 0, I can think of a neural net, which has a single number of input and outputs and can add hidden layers.
Yeah, no, that's a good point too. So actually a neural net would also go in there. So instead of having t equals 2, I might have t equals 1,000, like a whole pile of inputs going into my first neural layer and coming out of that layer. But you're right, I could just keep making the neural network deeper and deeper and deeper, and my number of inputs and outputs doesn't change. It's a good example. Thank you. Okay, let's see. Okay, so we try to find an example for p equals 0.5. So p equals 0 is kind of like great locality. Super local communication, fantastic. P equals 0.5 is actually still pretty good. So good locality. Like, the wiring complexity is not that high. So chip architects like this, people writing CAD tools like this. Do you have any thoughts of what might lead to p equals 0.5? Yeah, what do you think?
I have a guess, but architecture.
A MUX architecture. I haven't thought about that one. So you're thinking, so how are you thinking of that?
It's logarithmic, right?
Sorry, what's that?
It's logarithmic.
Is logarithmic. So as I put more muxing
Yeah.
in,
Of the gates
okay.
is the increase in the input, and 0.5 is square root, so it would
Oh, so you're thinking of a lookup table. Is that what you're saying? Like, you're thinking MUX architecture kind of like the lookup table, where the number of inputs to the lookup table will grow logarithmically with the size of what's in it.
be 0.5
Yeah.
increasing response.
So I'd say a lookup table is even better. If we're making a bigger and bigger lookup table, it's better from a wiring point of view. It's basically because the logic's growing so fast. But you're right, the inputs would grow logarithmically. But it'll be that's even less than 0.5. So what do you think?
Network switch.
So a network switch, yeah, so anything that has, like, you think maybe a two-dimensional kind of structure of a network switch, like this many inputs come in, this many outputs go out. Yeah, so basically things with a kind of a natural, can be laid out in 2 dimensions, actually have 0.5. So I'll give you one example that is similar to that, but one that is easier to draw, is like an SRAM. So if I build an SRAM, you have word lines here. So this is like the SRAM core. So you have word lines, and those word lines go across and they select a bunch of SRAM cells. So I have SRAM cells under these, and so on. And then I have bit lines between them. Okay, so you activate the word lines. One set of these is activated. They start pulling apart the bit lines beside them, and you read out your outputs here. Okay, so your inputs to this array is basically number of word lines plus number of bit lines. If I take the area of, like the number of SRAM cells, the amount of stuff inside of here is basically word lines times bit lines. So phrased another way, like the number of terminals is therefore proportional to the number of SRAM cells to the 0.5. It kind of makes sense. Basically, I've got an area, and all the input and output is on the perimeter. So it's kind of like, what is the relationship between the perimeter and area of a square? The same thing would be true for essentially any kind of two-dimensional processing array, like a network switch too. So, so this is pretty good locality. Your input and output count is growing, but it's growing quite a bit more slowly than the amount of logic. You can also, this is harder to visualize, but you can have p equals 0.75. And this turns out to be around what you get with random logic, so control logic that's doing all sorts of stuff, with poor locality. Some control logic has a rent exponent less than this, but some control logic can have this kind of locality. And this actually gets, the wiring is getting more complicated. This you can kind of see how to lay out in a two-dimensional chip pretty clearly. This gets harder, right? Because the interconnect is growing faster than the perimeter of your block. It gives CAD tools more problems. It gives FPGA architects more problems. All right, so I'm going to try to finish this analysis, which might, well, okay, I'll pull the class. I can probably finish this analysis in 5 minutes, or you can see if you can hold it in your head for a week and we can finish it next week. Who wants to finish it next week? Okay, one, who wants to finish it now? Okay, actually a fair number of people. I was just like, who wants me to never finish it? Like just stop and just we'll never speak of this again. Because I was thinking if there are many people who didn't vote, that's the only remaining vote. Okay, so I'll try to, if you have to go, just take off, right? So I don't mean to hold anybody hostage, and it's all recorded. So, but yeah, if I can finish this in 5 minutes, it may be easier for you to keep in your head. So yes, if you are exhausted or have to go, I will not be offended, and you can always check out the video. Okay, so that was rent exponent. Okay, so this is what leads now to a negative. So the negative is basically, when I'm designing this hierarchical architecture, I'm basically picking a rent exponent. I am picking, as I go up the hierarchy level, as I get more and more stuff, how many terminals do I assume? I've actually picked the rent exponents as I was doing this. So you have to pick, let's call it the rent exponent for the architecture. Okay, so let's say, for example, the rent exponent for the architecture is equal to 0.5. Okay, so I assume pretty good locality, and it's basically what I did over here. So I'm going to use W to mean how many wires do I put in a channel at each level. So the level 1 wires, W level 1 is 2, okay, in my example over here. First level channels have 2 wires in them. And based on my rent exponent, I can work out, what should I do at every level. So W level 2, I have 2 wires, but I have twice as much logic now. At level 2, I don't have 2 logic blocks anymore. I have 4 logic blocks I'm connecting. So I got to double the amount, well, I've doubled the amount of stuff, but my rent exponent is 0.5. So the amount of terminals that I need, number of wires that I need, is 3. So does that make sense? I had 2 wires in this channel. Now I've got twice as much stuff. How many terminals do I have to support? Take the square root of that twice as much stuff. Okay, W of level 3 would be equal to 2 wires times, now I got 4 times as much stuff. Take that to the 0.5, and I get 4. Okay, and that's exactly what I drew here. My level 3 wires, I had 4 of them. Okay, so far this all seems fine, right? Let's see. Is there any way I can do this? Maybe not. Okay, so that is, what I've done is fine for any circuit that has a rent exponent of 0.5 or less. 0.5 is perfect, right? The circuit's going to perfectly use all my wiring. Less than that, I got more than enough wiring, so maybe I wasted some area, but it's going to work. But what if I said that you can have random logic, for example, so control logic that has higher exponents. So let's say P equals 0.75. Okay, so there will be cases like that. They're not going to be everything. So now we're going to write out not W, but demand. So instead of W, which is how many wires that I build, we have demand from this circuit. So the demand at level 1 is going to be 2 wires. Okay? The demand at level 2 is going to be 2 wires times, I got twice as much stuff at level 2. My rent exponent is 0.75. So if I calculate that, that's 3.4. Okay, it's a little more than the 3 wires that I built, but you know, maybe that's fine, kind of within round off. My demand at level 3 is equal to 2 times 4 to the 0.75, which is equal to 5.7. Okay, so I round that off, that's 6 wires, and I only built 4. So that is not going to route now. Okay, this one, maybe it rounded down to 3 and I was okay. This one's not going to be okay. So this won't route. Which makes, you know, customers, engineers unhappy. They bought this chip, their design doesn't fit in it, what do? And it's a problem too. It's a problem obviously because they usually figure that out kind of pretty late in their design cycle. They actually have been writing HDL and now they're running it through place and route, and place and route says even though you have enough logic, you don't have enough routing. And you figured it out kind of late, so it's not just that it failed kind of late in the design process, so that's painful. So what do? Does this just mean like this architecture cannot possibly handle this circuit? Because there are circuits like this. Does it mean I have to use well, I could change my chip. So I could say, I didn't build enough routing. So I'm going to go back, and the next time I architect one of these chips, I'll assume a rent exponent of 0.75. I'll make all the channels wider. If this is happening to most of my user base, then that's what I should do. I just need to widen my channels next time because tons of people are having this problem. But if most people are okay, you know, they had rent exponents of 0.5 and they were doing fine, then I'd probably rather not do that because widening my channels increases the cost of the chip. So there is a problem with doing that if only a few people need it. So let's say I'm in that case. I actually think most people don't need the channels to be this wide, but this customer does. Is there anything I can do? What do you think?
Introduce some control-specific routing.
Well, so that's, I guess, adding more routing, and I guess you're saying more control-specific. I'm not quite sure what it means. Like,
Some routing that is specific for mapping control circuits onto.
okay.
It's a very small part of the overall routing.
Okay, so we'll come back to that later. So there are some things you could do there, and I guess that also goes into the general bucket, though, of adding routing. Is there anything I could do just? Well, usually when FPGA vendors make a chip, they don't just make one, they make a family. So they make some small ones, some medium ones, some big ones, okay? And they all kind of have the same architecture because it's really expensive to develop an architecture and a layout. But they usually have, could I move this person to a bigger chip, right? So that is something you can do. So if I move them to a bigger chip, let's say a chip that instead of 3 levels of hierarchy, it actually has 4 levels of hierarchy because it's twice as big. At level 4, okay, so I needed to buy a bigger chip to get this. The number of wires I have is 2 times, the amount of logic I have is 8 times the base level. My rent exponent was 0.5. If I put all that together, I get 5.7 wires at level 4. So a bigger chip will have a routing channel big enough to handle this. It's 1 level higher in the routing hierarchy in this case. So this is basically with the level of hierarchy that has 8 logic units has enough wiring to support this circuit's demand when it's only using 4 logic units. So it means I could put this circuit in this bigger chip, but I can actually only use half the chip. I got to leave half the logic blocks unused so that I'm basically sort of skipping over some of the routing hierarchy levels and just getting up to the fatter ones higher up. So this is, but, only 50% utilization. So this is an interesting problem with these hierarchical FPGAs. You have to essentially pick a rent exponent. How wide do the routing channels get as you go up? If you pick too high, you kind of waste a lot of area that nobody uses. If you pick too low, you'll get a fair number of people who have to underutilize the device. And they actually have to underutilize it a lot, right? Like this particular design that only has a rent exponent of 0.75 instead of 0.5, it can use only half of my device without exceeding my routing. So it's a tricky trade-off. Okay, so that's it for today. We'll talk a bit more about next week about some of the pros and cons of this and then move on to the alternatives. Thanks, everybody.